going to ask me that question? Great question, because once you see log n, every time you're going to have it in the back of your mind when there's something random. Couldn't I improve it with power of two choices? Good first instinct. But let's do something a little bit more of a zag away from this, which is what happens when no one actually knows the full set of caches? That's a pretty unrealistic assumption that not only is there some global answer to which caches are alive, but that every single person actually knows what this set of caches are, so that they can apply their own hash function. Now let's remove that assumption and let's do it using consistent hashing.
So you're saying that so the client computes the hash, the function from B to C,
yeah.
But different clients will compute it differently.
Exactly, right? So you think about it instead as, instead when you choose this root to leaf path randomly, you can apply the hash function to each of those things. That tells you the sequences of requests you're going to make. But then the issue is no one has actually one consistent view of what the set of caches are. Let's use consistent hashing for that. So this is a very different kind of scheme, right? Because now in this scheme that we're talking about, originally consistent hashing was what if the number of servers changes? But this is not an issue with number of servers changing. Maybe it's just impossible for everyone to agree upon what the answers are. So I like it because it's a very clever way to use this idea of consistent hashing, which is a gem in its own right. But now, let's talk about the setup for this inconsistent world. So the inconsistent world, I think that was one of their fanciful titles of a section of this paper. So what we're going to do is, what if everyone has a different view? So what we're going to do is we're going to assume there are C1, C2, up to CL views, which all of these are sets of the actual live caches. It would be bad if they thought some cache was alive which just doesn't exist. That's a separate issue. But what if they just know some subset of the live caches? And what we're also going to require is, if they knew nothing, if Ci was empty, that would be bad, right? Very little we can do. But all we're going to assume is that for each of them, the fraction of live caches that they know about is at least 1 over t, for some parameter t. So can they still come up with a good routing scheme based on random trees using, in this setting where no one really has a consistent view? So the idea is that now, the way that this scheme is going to change is that what we did was we chose, when we're creating a request, we chose some root to leaf path. And now what's going to happen is each of these clients, each request, is going to use some hash function from a consistent hash family. So instead of applying this hash function h from the virtual nodes to the caches, it's instead going to apply the hash function from the virtual nodes to the set of caches that it knows about. So that transforms whatever this path is in this virtual tree into a path on the caches that it knows about, right? Based on its worldview. That in turn induces the same protocol, because all you do is once you fix that sequence of caches, you ask the first guy, if he has it, great. If not, he asks the next guy on whatever the path is. And you tell him the path of things that you want him to request along. So the issue is that why does this scheme still work? So the fact that it's good, we proved over there that each cache is not asked too many times. Just because of balls and bins, that it doesn't map to too many different virtual nodes, and because each virtual node can't be asked too many times before its descendants all store the answer. So what we're going to do is we're going to show that this actually does work, and that'll be the remainder. Yep.
Are we assuming that that set of caches is random for each client, or?
No.
So wouldn't the
but our
worst
hash
case,
function is random.
wouldn't the worst case just be everyone knows about the same subset of caches?
That would be good.
Because then we only have a factor of t overhead.
Yeah.
We're trying to prove we only have a factor of t overhead.
So that would be good if everyone only knew about the same subset. The issue is they could know about different subsets that don't even intersect, right? You know, what if t is 100, and then, you know, 100 of these guys might actually all be disjoint. They don't even know about the same things, but can they together create a scheme in spite of their inconsistent worldviews that actually shares the load pretty equitably? All right, I want to get to the punchline, so let's do this.
Basically, if things are simple, like it's equivalent to small, small number of times. What we want to prove is that no is
Yeah, I was going to ask you about that, but that's all right.
Everybody workers with this one class. Everybody knows that. They all like sometimes skip over all the intermediate caches and also that one like ridiculous.
Okay, let me tell you the lemma. This is all we have to get through for the rest of the time. So what I'm going to do is I'm going to say,
But what if people actually also see the same cache, like in the
if there are at most n total requests, then high probability each cache is asked. And I'm going to prove slightly weaker bounds because I'm going to do it much simpler than the original paper. Is asked at most dq t squared log squared of nl. You can ignore L. L is the number of views. You can say that that's at most n, the number of page requests, so that's fine. So don't worry about that. The important thing is remember D is the area of our tree. Q is this counter which saturates. T is the fraction, 1 over T is how much each view contains of the actual live caches. And this is what we want to prove. And actually, this entire thing is going to be broken down into 2 parts. Let me tell you part 1. Part 1, we just want to answer the question that's analogous to what we did before, is how many virtual nodes is a cache responsible for So this last time was just balls into bins, but the key difference here is that we care about over all the views. Okay? So before there was only one view, so we just had balls into bins. But now what I care about is, for a given cache, among all of these different hash functions that we apply from our consistent hash family, for each one of the views, what's the set of all virtual nodes where this cache could appear for some view? That's clearly important because it shows how many different actors whose parts it can be playing in this, right? So this is actually not so bad, so we're going to prove this first part, and we'll prove the second part too, which will be very similar to it. Let's answer the first part. So what I'm going to do is I'm going to fix some cache I. And we're going to fix where it's mapped to. So let it be mapped to ti, some location. What we're going to do is we're going to consider the interval I, which is the following. So we're going to take ti as the right endpoint, and we're going to consider this interval I, which is size, let me write it up here so there's a little bit more space, 10t log nl over n, right? So this is kind of reminiscent of how we bounded the max length of the interval that a node is responsible for, except now instead of having something log n over n, we have this extra t factor. Yep?
Is there any relationship between ti and t?
No, there isn't. Let's change this to xi, just for simplicity. Good. So let's continue this thought experiment. Good, I left enough of the board this time.
More than D doesn't.
If we didn't have pieces here, we could have every solution.
Okay, so what we're going to do is now let's also, fix some view, Cj. And what I claim is that the probability that no cache in Cj is mapped to I, which is this interval whose right endpoint is xi, where the ith cache goes, and it has this length nt log n L over n. What I claim is the probability that no cache is mapped to this is at most 1 minus 10t log n L over n, the size of Cj. This is at most the same thing, but raised to the n over t, which is in turn at most 1 over nl, let's say to the 10. It's not so important what these exponents are, but the important thing is that, see, I only have n over t caches here. That's why I needed my interval to be longer, so that I have a t over n here, which matches the other t over n. So then I get something that's still inverse poly small, right? Now, the important thing is here, now what we can do is we can union bound over all of the views. And what we get is that with probability, at least 1 minus 1 over n to the 10, we have the fact that in each view, each of the L views, Cj, maps at least a cache to I. So what's the significance of this is that if we actually take I, then this interval, no virtual node that's mapped outside of the set is the cache ever responsible for, because in every view there would actually be something else mapped within this interval that would instead be responsible for it. Yep?
Is there also supposed to be an L for the 9 conducted on there?
Yeah, I'm being very sloppy with the bound. There would be an L to the 9th, doesn't really matter, because I'm not going to use it beyond union bounding over L, but sure. Yep.
What is I? Or T?
I is this interval.
That's that interval.
Yeah,
Okay.
exactly. And T is this lower bound we have that each view is at least, 1 over T fraction of all the live caches.
Okay.
Was there another question?
The uppercase T is actually an I.
Okay.
Yeah. Exactly. Very bad at handwriting. Various points. It's amazing I passed elementary school. All right, so now we're actually in business, right? Because we have a bound on how many virtual nodes a different cache could be responsible for. So what I claim is that cache I is not responsible for any virtual node outside I. Okay? So that's the key point. And now we know how long I is. So we know it's 10t log nl over n. So that means the expected number of virtual nodes that it's responsible for is we just take the length of that interval and multiply by n. So what this gives us is actually what you can prove is that for turnoff bound, since we already have an extra log there, we don't need to lose another log. And what you can show, which completes part 1, is that using turnoff, and I'll just leave this as something you should check to get familiarity with turn-off bounds. But with high probability, no cache is responsible for more than O of T log NL virtual nodes. Okay? Guys, you can also union bound over all of the different caches. That's why I have this extra, 1 over n to the 10 down there. It's just that I can do that. So this is part 1. Part 1 is we need a bound on how many of these different virtual nodes somewhere in this random tree can actually be mapped among any of the views to a particular cache that we care about. So the remaining part is what we want to do is we want to consider a single virtual node and understand how many caches it can be mapped to among all the different views. So one is how many caches, for a cache, how many virtual nodes can it go to? The other is the complementary property of, for a given virtual node, how many caches can it be among the different views? So that's actually the only remaining part about this. So I'll do this over here, and then we'll actually be able to finish the proof. But really the proof of the second part is basically the same as the first part. So part 2 now is really asking a question: how many caches can be mapped to from a single virtual node? And here again, the issue is that it's over all of the different views, right? So we can do the same thing for part 2 to get a bound on it, which is that we can fix some virtual node, let me call it J, and where it maps to. Let's call that Vj. And what we can do is we can define a new interval I, whose length is the same exact thing, 10t log nl over n. And now what trick? What should I say? Yep.
With high probability, no cache outside of I will ever be responsible for VJ.
Exactly. That's even jumping one step further, which is with high probability, each view maps a cache to I. This is really just doing the dual of this thing. And so what that means is exactly like you were saying, is that it tells us that any cache outside I, J is never responsible for, is never gets mapped to. So what this gives us at the end of the day is if you applied the same turn-off bound, how many would you get? You get the same type of thing as before. You get OT log NL. So now we can do the same proof. The idea here is that we know that each of our caches can only map among all the different views to at most T log n, I'll ignore the L, T log n different virtual nodes, and each virtual node can map to at most T log n different caches. So if you think about a particular cache, it can only be asked because it's playing the role of some virtual node, but whatever that virtual node is, how many times can you actually send requests through it? It's not D times Q anymore like we had before, because each one of its descendants could actually be playing the role of many different caches. But each one only plays the role of at most T log n different caches. So actually the bound we get is the same thing that we had. We had this D times Q, except we now multiply by how many different nodes a cache can map to virtual nodes, and for each virtual node, how many different caches they can be. So it's actually the same verbatim argument that we did last time. So we'll end it there, and I'll tell you a little bit about what we're going to cover next time. Is we're going to cover distinct elements and heavy hitters. We're going to talk about what you can do when you can't actually store the amount of data coming through, period, can you still understand the properties of these data streams? So this will be some of the basics of what's called streaming. It's a big industry these days, and we're only going to touch it. All right.